So here's how you can approach using Excel to creating energy bar charts. This would be for the teacher, the moving teacher. We're assuming the balloon has a mass of 1/4 kilo. I'm assuming that you stretch your launcher bands 1 meter. The initial velocity, that's the total velocity, would be 15 meters per second. And then at the very, very peak that all there is horizontal velocity. And this is shot at 45 degrees. Each of the components, both the Vx and the V horizontal and V vertical, are 10.5, and you do the Pythagorean theorem and you'll get the 15. So anyways, a little bit of trig gives you that. And then I don't have it written down here. I did it somewhere else. I forget what number I used. There is a final velocity because it does fall an additional little bit between where it was launched from and the ground, so it's actually going a little bit faster than 15. I think this is like 15.4 meters per second. An average spring constant for launcher systems that have the commercial kind of pull to them, well, they come in different pulls, but one of the ones that I've measured before is 150 newtons per meter. And then if the hypotenuse of your launcher is 1 meter, then that would mean that the vertical distance that it left your launcher at is 0.71 meters. So that's these values that I've shown right here. And then I identified here are the various ways that you can calculate the various sorts of energies. And so what I've shown here is first the unload to load. And so what I did in all of this is I put zeros for the energy stored in the gravitational field, in the motion, and in the spring, all to be 0 to begin with. And then you come along and through working on the system, you add energy, and in this case 75 joules of energy to the system. So how did I know that? Well, what I did is over here in the spring, because that's where the energy gets stored, is in the springiness of your launcher, that I put in an equation. I'm trying to put in an equation. And so what I did is the way you calculate energy stored in a spring is it's 1/2 K, which is the spring constant, which you notice is this 150 right there, times the x squared, so it's 1/2 kx squared, and x is the stretch, and so you notice that the stretch is in cell B2, and you see how those two cells are highlighted, so that's where I'm collecting my data. And so that's where that came from. And then for this one, since I knew that the energy stored in the spring was 75 joules, I just typed in 75 joules here because it had to come from somewhere. And then what you do in the next step is you go from loaded to launch. And so whatever you had over here is what you would start with over here. So I start with the spring energy initially, and then when it leaves your launcher, just as it's leaving the launcher, it is above the ground, so there is some energy stored in the gravitational field between the balloon and the Earth, and there's some energy stored in the motion, and so those are those numbers. And again, if you look, you'll see that gravitational energy storage is mass, so that's cell B1, which you see highlighted there. So it's mgh, so it's the mass times the gravitational constant times the height. So that's in cell B7. And in a similar fashion, that if I want to calculate the kinetic energy, the energy stored in the motion of the balloon, it's 1/2 mv squared. And so you'll see that I have 1/2, and then B1 is where the mass is, and then B3 is where the velocity is, and that's all squared. Now, I have not given you an equation for, oops, I don't want to mess stuff up. I just messed it up. Let me escape and make sure that doesn't mess up. Okay. There's no direct measurement of dissipated energy, but I hope it makes sense to use. If I start with 75 joules and then I end up with 1.7 and 28.1 stored in the gravitational field and the motion, that the rest of it must have been dissipated. So you'll see what I did here is I took this cell, which is the G15, and subtracted from it this energy and this energy, and so that's how I got the results. Moving back here, then if I wanted to do the next one, like launch to peak, that what I did is I just made this series and I copy it, and then I'd come down here and I'd paste it. And if we did, again from launch to peak, that the launch, what I would probably do is just say equals, and then click on that cell and call that good. And I do the same thing for the kinetic energy, because the final kinetic energy of the previous step becomes the initial energy. Now, of course, the energy that was dissipated is gone from the system, so it doesn't show up here anymore. And so what I would do is determine what the kinetic energy is at the top, because remember, it's at its peak, and so I only have horizontal velocity. So what I would do is 1/2 mv squared, but with a different v, so that'd be 0.5 times mass times this peak velocity, and then I would square it. And then the way that I would know how much gravitational is by, again, looking at the differences between what's on the left and what's on the right. So what I would do is say this is going to equal whatever I had here on this left-hand side minus the kinetic energy. And so that's how I know what that would look like. And so you'll notice that the gravitational energy has gone up, the kinetic energy has gone down. And we've asked the question before, well, are they 50-50? Well, you don't know. It depends on the system. Now let me go ahead and pop in zeros for all the ones that should be zero. And again, we're assuming there's no air resistance, so I'm considering there's no dissipation. Now if you want to create a chart, that what you would do is find charts somewhere on your Excel, because different operating systems look different in different versions. But what I'm going to do is I'm just going to choose columns like that. And so you'll see that I started out here with a little bit of gravitational and a lot of EK, and then now it's switched over. I get rid of this because they're all series 1. The other thing that I have a tendency to do is, just so that it makes, that the chart itself makes sense, that I go to the chart layout area. First of all, I do a chart title. I overlap title at the top, and what I'll say is launch peak, so that this graph is meaningful. And then what I would also do while I'm here is the axis title, and I would have, for the vertical axis tile, rotated tile, because a good graph should always have the units. And so these are joules. And so that's pretty spiffy, huh? And then you can copy that into your technical document and be good to go. And so, it's something that you can do. The 3D cylinders, here I did 3D cones, so whatever floats your boat. Just do what makes sense to you and what looks pretty to you, and you can change colors and all kinds of stuff if you want to just go all crazy about it. So I hope that made sense, and let me know if it doesn't. Bye-bye now.